Hey everyone, today I'm going to show you guys how to turn a quadratic function that is in standard form into a graphing or vertex form. Now to do that, we're going to do a method called completing the square. Now notice that the graphing or vertex form has something that looks like this, where it says x plus 3 quantity squared. Now geometrically, what that looks like is a perfect square where the length and the width are exactly the same. In this case, we have x plus 3 times another x plus 3. So that is a perfect square where the length and the width are exactly the same. Another example would have been like x plus 4 times another x plus 4, or x plus 5 times another x plus 5, or even 3x minus 2 times another 3x minus 2. As long as the length and the width are exactly the same, we have a perfect square. Okay, so let's go ahead and begin. We have a quadratic function in standard form, and we're going to turn that into vertex form. To do that, we have to make a perfect square. So what do we have here? And let's use algebra tiles to help us understand the process of completing the square. So we have one x squared tile. Okay, now that is a perfect square as well because both the length and the width are length x. So that is a perfect x squared tile. Now we also have 8 x's. So here are the 8 x tiles. Okay, so now we're going to use those tiles to build a perfect square. So we see an x squared tile over here, but to stack the x tiles, they either have to go on the top of the x squared tile or on the side of the x squared tile. So how do we build a perfect square with just 8 x tiles? Well, I can stack maybe 3 on top and 5 on the side, or I can stack maybe 6 on the top and 2 on the side, but none of those will build a perfect square. Now remember, both the length and the width have to be exactly the same in order to build a perfect square. So if I have 8 x's to work with, how many should go on each side? Well, the answer is 4. To build a perfect square, I have to stack 4 x tiles on the top and 4 x tiles on the side. That's because what we just built is the same length and same width. X plus 4 times another x plus 4. So what we just did there was we took 8 x's and cut that in half. So that's why we have 4 on the top and 4 on the side. Okay. So just by even looking at this, we already know what the square looks like. We know the square's length and the width. We see that the square has a length of x plus 4 times a width of another x plus 4. So really we know that this has an x plus 4 times an x plus 4 or x plus 4 squared. However, notice we did not complete the square yet, because we're still missing something called the ones tiles to fill or to complete the square. So how many ones tiles do I need to fully complete the square? We have 21 ones tiles. So how many of these ones tiles do I need to fill in to make a perfect square? Well, I know that there's 4 over here and the length of 4 over there. So I need 4 times 4, which is 16 ones tiles. And there you go. But I had to use 21 ones tiles to make that perfect square, but I need 16 of them. So how many ones tiles do I have left? If I need 16 but I had 21 in the beginning, then 21 minus 16 then is 5. So that means I only had 5 left over. And there you go. So then how do we write this as a vertex form? how can you write this as an expression? So here's what this looks like. We had one x squared tile and 8 x's, but we cut that in half to make a perfect square. So we have the length and the width to be exactly the same of x plus 4 times another x plus 4, or we're just going to say x plus 4 squared. However, to build that perfect square though, we needed 16, but I already had 21. Since I already had 21, but I need 16, I have 5 left over. So the remainder is plus 5. And there you go. We just wrote an equation in vertex form, given a standard form, by using the method called completing the square. So let's go ahead and try another example. Okay, so here's another example of a quadratic function in standard form, and we're going to turn that into vertex or graphing form using the completing the square method. So let's go ahead and use the algebra tiles again to help us figure this out. So we have x squared tile. Then we have 6 x tiles. Now to build a perfect square, how many x tiles go stacked on the top and stacked on the side? Well, do I need 1x and 5x on the side, or 2x stacked on the top and 4x stacked on the side? Well, again, remember, a square has all the same lengths on 4 sides. So we need to have 3 stacked on the top and 3 stacked on the side. In other words, since we have 6x, we gotta take that and split it in half or divide by 2. 6 divided by 2 is 3. So that means we need to have 3x stacked on the top and 3x stacked on the side to build a perfect square where the length and the width are equal. Okay, now just by even looking at this without finishing the square, we can already see what the length and the width should be. The length should be x plus 3 times the width of another x plus 3. So we have y equals an x plus 3 times another x plus 3 square. However, to build that perfect square, how many ones tiles do I need to fill in? Well, since we know that this portion right here has a length of 3 and the width of 3, we need 9 ones tiles. So, 9 ones tiles. The problem is, I have 7 ones tiles. I have 7 ones tiles, but I need 9 to fill that in. So it looks like I need to borrow some tiles. So if I have 7 ones tiles, but I need to borrow or take 9 tiles, I need to borrow 2 more. That's because 2 of them are missing. Okay, so since 2 of them are missing, we can now write this as x plus 3 squared, but I need to borrow 2 more to complete that square. And there you go. We just turned another quadratic function in standard form into vertex form by completing the square. Let's try one more example. Okay, so now here's one more example of a standard form, and we're going to turn that into vertex form. So let's go ahead and complete the square. So I'm going to use a generic rectangle to help us figure this out. We know that there's got to be an x squared tile over here. And I have 10 x tiles. Now to build this perfect square, how many x tiles do I need to stack on the top and stacked on the side to build a perfect square? Well, we know that they have to be equal on the top and equal on the side. So 10 divided by 2, or cut in half, is 5x stacked on the top and 5x stacked on the side. So immediately, just by even looking at this diagram, I already know the length and the width of this perfect square. The length must be x plus 5 times another x plus 5. And it makes sense because x times x is x squared, 5 times x is 5x, and so forth over here. Okay, So immediately I can already see what the perfect square looks like. These two should help me make an x plus 5 squared. But how many ones tiles do I need to build this perfect square? Well, 5 times 5, I need 25. However, I only have 21 ones tiles. So there's a problem. I only have 21, but I need 25 to build this perfect square. So it looks like I need to borrow some. So 21 minus 25, I am missing 4. Therefore, I need to borrow 4 to build that perfect square. So the remainder, or how much we have to borrow, is minus 4. We need to borrow 4 more tiles to build this perfect square. And there you go. This is another example of a standard form turned into a graphing form using completing the square method.